The failure modes of penalty methods for collision response are well known. Given a penalty force of any stiffness, there always exists a relative velocity high enough to induce failure. This has led researchers to develop methods that sacrifice physicality for a robust collision response. We revisit the problem of collision response for deformable bodies by setting forth 3 criteria. First, the method must be safe, and that it disallows all interpenetrations. Second, the method must be correct and obey physical laws. And lastly, the method must never fail to make progress, so that simulations complete in finite time. Our method works by employing discrete penalty layers, a set of nested penalty forces that grow increasingly stiff as colliding objects approach. Take, for instance, this particle approaching a fixed wall. As it comes within proximity of the wall, a relatively weak penalty force is activated, repelling the particle. However, this particular particle is stubborn and travels at a high enough velocity to tunnel through the penalty force. In this case, a second, stiffer discrete penalty layer is activated to assist the penalty force at layer 1. If the particle persists, this process of activating increasingly stiffer forces continues until the collision is resolved. Since this is a penalty method, friction is easily incorporated without the need to solve complicated systems, allowing for a wide range of expressive behavior as seen here. In this simulation, we prescribe a cannonball to fly into a sequence of densely hung curtains. We demonstrate that our method is robust even when the velocity of objects already in contact changes drastically by giving the cannonball an extra kick midway through its flight through the curtains. Because our method preserves physical causality and guarantees an absence of penetration, we observe steady, penetration-free stacking and efficient, accurate handling of fast motion. This simulation was run with only stretch damping, a mode not excited after the initial frenzy. Observe that even after many oscillations, the curtains continue to oscillate back and forth and will continue to do so after long run times. We employ this method on several challenging scenarios. Here we tie a reef knot out of ribbons. Notice that the knot remains stable as the penalty forces and the internal forces struggle to find equilibrium. Even after yanking the knot tight, the cloth remains artifact-free and ready for more simulation. This bowline knot illustrates the complex interaction experienced as the knot tightens around a crumpling cylinder. Our 3 criteria are required to capture the interplay between the cylinder's internal bending forces, the strong contact forces, and the forces inside the tightening knot. By using proximity-based penalty forces, our simulations can run even with extremely sharp edges and corners. Each of these spikes consists of only 4 triangles, yet the cloth stably rests on top, despite the notorious troubles associated with this type of geometry. Here we bombard the spikes with stiff balls. Notice the bounces and ricochets made possible by respecting the physical laws of conservation and causality. We further test robustness by cramping geometry into the tightest space possible. Even during the violent pressing of the scripted walls, all forces remain stable. We compact the bunny into the smallest width the geometry allows, with no instabilities. Plasticity allows the bunny to retain her new, leaner shape. In this video, we saw a method that guarantees safe, penetration-free simulations that obey physical laws, while still completing in finite time. Thank you.